Hello there. In this problem, we're going to go on a circle theorem journey. There's going to be a lot of steps here, and we're going to solve for all of those variables, x, y, and z. Given the sketch here, I only know two lengths, 8 and 9, but I know various ratios of other lengths. For example, this chord here is being cut in a 2-to-1 ratio, and this segment here is a third the length of this one, and that's 3 times as long as that. And that section there is twice as long as that one, and it has a point of tangency. So we need to be strategic about how we start setting up our circle theorems. First one that we're going to do is, because I know this whole length in here, I'm going to use that, and just that portion, so I have this chord and it's intersected by this other chord. So as I go out from that intersection point P to the circle, it's 8 on one side and 9 on the other, and their product has to equal the distance on the other one, which is going to be y, times the distance to where it hits the circle there, which is going to be 2y. I can multiply those together, divide by the 2, and solve for y. So I actually know this length now. This y, that is length 6, and this 2y, that must be length 12. At this point, the problem gets pretty tricky, because to now use these lengths that I know, well, it's going to extend outside. I have this z, so I got to be talking about this secant and what would then be this tangent, but I am going to have two variables here, x and z, and we don't know their relationship. So it feels like too many variables, but I also have a secant and a tangent on this side too. So I'm going to write down relationships that I know are true with all of the variables and then see what we can do. Starting on the left-hand side, the whole trick with tangents is that you go to the point of tangency and then you go to that point again. So you're actually doing the distance x times x, or x squared. And that has to equal the other one, the secant, where you go to the circle, so that's distance z, and then you go all the way through to the circle again, and that whole distance there is z plus 12 plus 6, or z plus 18. So I can multiply through, simplify that, but it feels like it has too many variables at this point. So I'm going to stop, and I'm going to approach it from the other side. So over on this side, to the circle here, to that point of tangency, I get 2x, and then I'm going to go to that point of tangency again, that's another 2x, and that has to equal this distance, 3z, to the circle again, all the way through to the other side, and that's 3z plus 9 plus 8, or 17. So multiplying through, I get that. Now this is actually a system. You may not have seen systems quite like this before, but it's got two equations, two unknowns. There's actually going to be a trick for solving. So let's label this equation 1 and equation 2. I need to get them to line up. I'm actually going to quadruple equation 2. So doing that, I'm going to wind up with 4x squared equals 4z squared plus 18 times 4 is 72. Z at the end there. And the nice thing about this is that those x's line up perfectly, and I can subtract them. So now I got it down to just one variable with z's. It's a quadratic, z squared and z, set equal to 0. No need to use the quadratic formula, we can use zero product property. So factor out a z, I get that. Either z is 0 or the inside part there has to be 0. So solving that one, move the 21 over and divide by 5, and we get 4.2. So that's equal to 4.2. Okay, so we got what our length z is. And if I triple it, I can get this length over here, and that will be 12.6. But ultimately, I wanted to know what x was, so I can go back to one of these previous equations that had an x involved in it. So like this one's pretty good. I think I'm going to want to use that one. Looks like that was equation 2. I called that first one equation 2 and that second one equation 1. Oh well, doesn't matter. Alright, so we know what z is, so let's plug that into where we see z in that formula. So I get this whole mess. Now we can expand that out. I'm going to need a common denominator, so I can multiply both top and bottom here by 5. And then add, add those things in the numerator together. So x is going to be the square root of this whole thing. Now, there's a little bit of a, I don't know how much of a shortcut, but you know, we want simplest radical form. This number here, 2,331, that's actually divisible by 9, because 2 plus 3 plus 3 plus 1 is 9. So we can, you know, kind of build a factor tree. I got that 9 there. And then that 259, question is that prime or not? I think... Okay, so 259 is not prime. It's 7 times 37, but those are both prime, and there's no pair. So when we take the square root of this whole thing, we're gonna we're starting to get interested in pairs. So the square root of 9 is 3. Square root of 259 stays as the square root of 259, and on the bottom the square root of 25 is 5. And what a lovely answer we have there. Alright, thanks for watching. Character and Scholarship for Life.